Hello, my name is Peter Trefonas. I'm a corporate fellow at Dow Electronic Materials Company. I am located in Marlborough, Massachusetts, and I've been working in the electronic materials industry since early 1985. As a corporate fellow in Dow, my job has many responsibilities. One of them is that I am a mentor to many technical teams, and I also work closely with my management. In these roles, my job is to guide the strategy in directions that are most productive and useful for the company. With the project teams, it's to help to resolve problems, help to catalyze ideas, help to develop the talent and develop the products to get them out to our customers' hands as rapidly as possible in the highest quality possible. Chemically amplified resist was a huge discovery, and it solved several problems that were confronting us at the time. At that particular time, the fluence of the photo tools wasn't that high, so we needed a chemical approach that we could still get all the reactions required in the film, but at the same time keeping the dose absorbed relatively small, which gives a fast photo speed, as it's called, which then gives a high throughput that is desired in manufacturing. Chemical amplification requires that you have a polymer, typically, which has protecting groups on it, which could be removed in the presence of a catalyst. The catalyst we use is an acid which is photogenerated. It diffuses around in its very local environment, causing deprotection reactions, which then give the solubility switch. It sounds simple at that stage, but actually to get an acid with the diffusion lengths that are required and not too great, and to limit its diffusion in its local environment requires the use of quenchers. And then the polymers themselves have become increasingly complex as we've added different kinds of protecting groups and polar groups and adhesion groups and etch-resistant groups to them. The entire process has caused quite a revolution in lithographic processing. Higher resolution has been possible, and at the same time we've maintained very high throughputs. The roadmap in front of us has less clarity than it used to have. And in the past 25 or 30 years ago, the pathway was very clear. At that time we were developing and improving I-line and 248 nanometer chemically amplified resists. The tool manufacturers were increasing the NA and making better capability tools. Other things were being simultaneously developed, such as metrology and etch processing and modeling and all the other things the industry needs. But the pathway in front was clear. At this point, it's not particularly clear. There are many options to resolving the challenges in front of us, and some of these options are complementary and some of them are exclusionary. And so I think there's going to be an increasing emphasis on chemical solutions that give further extension to 193 immersion lithography. That is the workhorse of the industry. It's tried and true, and these extensions will give the ability to give shrinkage of trenches and contact holes. They'll give the ability to smooth some of the line width roughness, for example, or perhaps the ability to do a frequency multiplication of one type of feature or another. I think in the next 5 years, we're going to see EUV take an increasingly bigger role, and photoresist chemistry will be very key to the success of EUV and achieving the photo speed, resolution, and line width roughness requirements of EUV. Other materials that are also used in the process, which include underlayers, top coats, and ancillary process materials are going to also become important. I think you're going to see a lot of improvements in those directions and work on Anti-reflective coatings continues to show improvements and customization to the specific needs of the substrates. Chemistry plays a key role in the enablement of microlithography, and because of that, the enablement of the progress of integrated circuits and electronics, and for that matter, the entire information age. Chemistry has enabled the ability to create patterns of exquisite fidelity and resolution, and because of this, we've been able to maintain a path along Moore's law in that we could keep making feature sizes which are smaller and get higher densities onto the chips we're making. And because of that, the progress has continued at a very steady pace for more than 40 years, and I think that pace will continue for some time period into the future. I believe it was very much enabled by chemistry.